Okay, everybody can hear correctly? Okay, so the committee members are Professor Angelo Iollo from University of Bordeaux. We have the second referee is Sam Taira from University of California, Los Angeles. He's connected on Zoom. Then we have Lutz Leschaft from LADIX, also connected on Zoom. Anka Belme from D'Alembert, and the two supervisors, so Pascal Frey and Tarane Sayadi. So Serena, you have more or less 45 minutes to present your work, and then we will ask some questions.
Okay. So thank you everyone for being here. So today I'm going to defend my thesis titled Numerical Method for Contour and Optimization of Fluid Flows. This work was done under the supervision of Dr. Sayadi and Professor Frey, and it was funded by the Institut des Sciences du Calcul et des Données here at Sorbonne University. So, to give some context, nowadays all the flowing contour in the industrial process can now be simulated with high fidelity using computational fluid dynamics. So, however, in order to reduce pollutant emission and increase the energy efficiency of this system, we need to control these systems in order to ensure optimal operating conditions. So, our goal is to modify a flow to match a desired output. From a mathematical point of view, what we do is we set a cost functional, which is the function that we want to optimize, and depends on the state variables, so the variables that governs our system, in our case our flow, and the control variables that are the variables that we use to modify the flow. Here, as an example, we can see the effect when we force the inlet, a nozzle inlet, in a gas turbine combustor. So here we can see the flame unperturbed, and here we're introducing some sinusoidal or periodic, square periodic forcing, and we can see how the flame changes shape. So we want to optimize this cost function. This cost function can have two shapes. Our goal is to reach the global minimum of the function, but as we can see here, when we have convex function, we have just one minimum. And when we have non-convex function, we have multiple minima. So our goal is to reach the global minimum, to optimize Rj. For doing this, we use optimization algorithms. Optimization algorithms are divided into two big categories. So we have gradient-based and derivative-free methods. And as the name says, gradient-based optimization algorithms are based on the knowledge of the gradient. So what we do, we start from an initial solution, and then we compute the gradient, and iteratively we move towards the optimum. The gradient can be computed in different ways, analytically using forward difference or adjoint-based methods. On the other side, derivative-free methods are as well iterative procedures, but here we have no knowledge on the gradient. So what we usually do, we span a lot of points in which we compute the function, and then according to some distribution, we increase the points until we reach a minimum. There are many derivative-free methods that depends on the way the algorithm search for the next points. Of course, these methods, they have some limitation. For the gradient-based, the most complicated thing is to extract the gradient. So as we said before, we can use analytic that is not always available for complex function. Forward differences that is not practical when we have too many control parameters. And adjoint-based methods in which the derivative can be computed with a single function evaluation. And when we use many control parameters, we don't encounter any issue. However, the convergence to the global minimum is not guaranteed because we rely on the gradient information, so we can get stuck in local minimum. And we still don't know how this case doesn't work very well when we apply adjoint methods to complex turbulent configuration. On the other side, derivative-free methods, they guarantee the convergence to the global minimum, and they are applicable to the turbulent configuration, but this requires many function evaluation, and this is also very complicated when we have too many control parameters. So this means high computational cost. what we can do is to use some strategy to reduce the computational cost and make this algorithm applicable and coupled with CFD simulation. So what we can use are parallel algorithms and multi-fidelity approach. Both of these methods can be used both for gradient-based method and derivative-free methods. For gradient-based, what we can do, we can parallelize the high-fidelity simulation in space or in time. And for derivative-free, what we can do is or parallelize partially the single simulation, so the single CFD simulation, or we can launch multiple simulations at the same time in parallel to evaluate the function at different points at the same time. When we talk about multi-fidelity approach, we want to build reduced order model that have dimensions lower than the high-fidelity model, so it's faster to compute. So for the gradient base, we can build a reduced order model for direct and adjoint or one or the other. This leads to an approximated gradient. And for the derivative-free method, we can build a reduced order model for the function evaluation, or we can build a surrogate surface, a surrogate model that approximates the objective function. What we did in this work during my PhD, I used gradient-based optimization with adjoint equations, and I applied temporal parallelization. And we investigated a little bit reduced order model, and we believe that reduced order model and the optimization procedure can be helped or facilitated when we have some information about the dynamics existing in the flow. So we propose an algorithm based on data for identify the dominant dynamics. These are the three main projects I worked during my PhD, but for lack of time today, I'm not going to talk about reduced order models. So the speech is organized in two parts. First, we will see gradient-based optimization with the adjoint configuration, and I will present the parallel time algorithm and some result, of course. And in the second part, I will introduce the first results we had with this data-driven identification of flow dynamics algorithm. So, in adjoint-based optimization, again, we want to optimize an objective function. And when we work with unsteady flows, this objective function can depend on time. Here we can see the contour line of the objective function. We want to get to the minimum. However, since we are solving some equation, we want that solution of our optimal problem lays on the subspace of the solution of the state equation, in our case, the Navier-Stokes equation, for example. So we have introduced a constraint in our objective function. So using the variational methods, we can form the Lagrangian to include the constraint in the objective function, here, multiplied by some Lagrangian multiplier that we call adjoint variables. Setting the variation of this Lagrangian with respect to the independent variables, so state variable, control variables, and adjoint variables, we can get to the continuous optimality system. So we do the derivatives with respect to the three variables. So first, we derive with respect to the adjoint variables, and we get our state equation, or the constraint. We derive with respect to the state variable, and we get the adjoint equation. And when we derive with respect to the control parameters, we get the optimality condition that is set to 0 and can be reformulated to get the gradient. So once we get to the continuous optimality system, to solve this system, we need to extract the discrete adjoint equation. Okay? There are two ways of doing that in the literature. We have the continuous approach or the discrete approach. So they differentiate, they're distinguished by the order of differentiation and discretization. So for the continuous approach, we start from the continuous primary problem, we differentiate, and then we discretize. For the discrete approach, we first discretize, and then we differentiate. The problem that we get at the end is not exactly the same. So in the continuous approach, the good thing is that the adjoint equations are not dependent on the solver. So once we have the continuous adjoint problem, we can discretize on a grid that is appropriate for the adjoint equation. However, we can get some inconsistency when we compute the gradient of a continuous cost functional. So we decided to use a discrete approach. We can have automatic differentiation that sometimes can have some issues, so not have the accurate result. So we use the methodology proposed by Fossas de Pando in 2012, in which the adjoint is extracted from the nonlinear simulation code. So basically, we take the operator of the nonlinear simulation code, and we do some manipulation to get the adjoint discrete equation. In this way, we don't have to change the grid. We have the solution at the same point, and we have the same efficiency of as the original solver, and this requires a low programming effort because we have all the operators. So now that we show that we chose the discrete approach, I will show the discrete primal problem. We start from incompressible Navier-Stokes to D. This is the solver we used all over the work. So we have inverse boundaries, meaning that we have to add an additional constraint and some source term as the inverse boundary forces. So what happens is that we add some Lagrangian points to simulate the surface of the solid, and then we have some interpolation here from the Cartesian to the Lagrangian points, and then we have these forces that are formed at the Lagrangian points. So now the inverse boundary forces are in our state vector, and we can get from here to the semi-discrete system of equation. So from this primal discrete, semi-discrete problem, we can get to the discrete optimality system. So same as before, we have the state equation, the inverse problem, adjoint equation, and the optimality condition, which is the gradient. So notice that the Navier-Stokes equation is a nonlinear equation. So to build the adjoint, we need to linearize the advection operator around the discrete solution. So once we have the gradient, what we do, we have the iteration. We start from a point, and every time we solve the direct, we solve the adjoint, we get the gradient. So we solve the system. Once we know the system, we move until we get to a minimum. I'll start showing some results of the adjoint solver and some optimization that we did. So we did the drag reduction of the flow around the circular cylinder at 3 Reynolds 200. So here we can see the flow, here we can see the time evolution of the drag. When we get to a stable limit cycle, we start the actuation. The actuation is done using as control parameters the velocity on the boundaries, so on the inverse boundary force points, sorry. Notice that in this case, we have 96 points. So my control vector has dimension 96, meaning that we are in a large parameter space, so it's convenient to use adjoint in this case. So we see the results of this optimization. We can see that the cost has been decreased. The distribution of the velocity, the inverse boundary velocity, sorry, on the surface of the cylinder, and when we do the projection on the surface, we can see blowing and suction effect, as we could expect. This is a steady actuation, so this velocity doesn't change during the simulation. Okay? So here we can see also the drag without control and with control, and the mean value is reduced, and the amplitude of the oscillation is reduced as well. The velocity distribution is pretty smooth. Remember, we don't have any correlation between the points, so we had to add the filter to ensure a smooth solution. So now, we solved so many iterations of direct adjoint, and we wanted to evaluate the time needed to solve these iterations. So when we want to solve just the primal problem, just the direct, it takes around 400 seconds. When we want to solve the full optimization loop, gradient expression, it takes more than the double. This is because, as I said before, each one of these iterations implies that we have to solve the direct problem from T0 to T final, and the adjoint problem to T final and to T0. The adjoint cannot start before, because to build the adjoint, we need to know the direct solution for the linearization. This implies that the direct and adjoint are solved sequentially. So for a steady problem, the time needed to solve the loop is at least twice the time needed to solve the direct. We wanted to minimize this time, so we use parallelization in time to accelerate the loop computation. So parallel in time algorithm, there are so many different methods in literature. They start more or less around the year 60 of the last century, and they're usually used to accelerate the direct problem. Some applications are seen in Mayday with the parallel algorithm, which was applied to control for control purposes. And so with this, they're divided in 4 main categories, but we will focus on the direct time parallel category with the algorithm from Gander-Gutter linear parallax algorithm. So the algorithm we'll use is based on this algorithm. So we'll introduce this first, so then we can go to the one we used. This one is applied on the linear direct problem. Okay? So we get an overlapping time domain, so we decompose the time interval. Here we have regular partition, uniform partition, sorry. And we want to integrate in parallel this linear initial value problem. What we do, we split this problem in inhomogeneous and homogeneous. Okay? So notice that the inhomogeneous problem is with 0 initial condition, meaning that the problems here in red can start to be integrated at the same time on different processors. Once we get to the boundary, then the last time solution of the inhomogeneous problem is used as initial solution to solve the homogeneous. Okay? When we split it on different processors, we can see then that the inhomogeneous is solved by one core on its own time partition, while the homogeneous is solved from the first here up until the end. At the end, the final solution is going to be the composition of the different solution. So, let's talk about the algorithm we used. Was proposed by Skin in 2022, and we extended this application to incompressible Navier-Stokes equation. So we want to use the linear para-exp. As we said, the direct problem is non-linear. So we use the linear para-exp on adjoint equation, which is by definition linear. So we set the optimization problem. We have our constraint, or our nonlinear direct equation, which is solved in serial, but still introducing a time partition, which is non-uniform, and you will understand why later. Then we form the adjoint equation, and now we apply para-exp. So we divide in inhomogeneous with 0 initial condition, and homogeneous with initial condition, the last solution of the previous inhomogeneous problem. So let's try to understand what happens here. So we want to solve the problem from T0 to T. We introduce a non-uniform time partition. Okay? So here we're using 3 threads. We start solving the direct problem up until T1 on thread 1. The other 2 cores are waiting. Once we arrive to the boundary, we have a communication. So the thread 1 sends QT1 to the next thread. And while the second thread is solving the direct equation, thread 1 can start solving the inhomogeneous adjoint equation backwards with 0 initial condition. And again, communication between 2 and 3. And while 3 is solving the direct, thread 1 and 2 can solve the inhomogeneous adjoint problem until the end. So now we are done with the direct problem. We still have to solve this little time partition here for the inhomogeneous problem. That's why the time partition has to be non-uniform in order to minimize the waiting time we have here. Okay? Once we arrive here, we want to integrate the homogeneous adjoint equation. Okay? But remember that we solved the direct on different cores. So the other cores 2 and cores 3, for example, they don't know the direct solution in core 1. So what we do a communication and then interpolate. Why? Because this was very memory expensive to communicate the full solution. So we took some points in the direct solution. We communicate just these points, and then we do an interpolation here in order to have the direct solution available everywhere. Once we are here now, so the first core doesn't have anything to do. Second core and third core, they are solving the homogeneous adjoint equation with an exponential integrator, and I'll show you why afterwards. And once we have the inhomogeneous and the homogeneous solution, we can build the total solution. Each core computes the cost and the gradient, and then that's the only thing they communicate between each other. So by the end, the communication cost is going to be a scalar and a vector that depends on the dimension of our control. So let's see what happens to the total time to the solution. This is the time when we use n core. So the first factor is the time needed to solve the direct solver, okay? So the time needed to arrive here. Then we have this time given by this time partition at the end. And then we have the time needed to solve the homogeneous adjoint equation. So we want to reduce this time in orange. So for the inhomogeneous adjoint, as I said, we introduce an uniform time partition to have a smaller partition at the end. And for the homogeneous adjoint, we can use it using an exponential time integrator. This allows the integration on coarser grid, still maintaining an accuracy on the solution. Okay? But we are working with incompressible Navier-Stokes, so we have some constraints. The equation is ADE. We need to do a projection step to be able to use an exponential time integrator. This work is now under review. It's just past the first review step in JCB. So why we need to add this projection step? This is a general linear initial value problem. We see that we can write the solution of this problem like this when A doesn't depend on T, and we get an exponential matrix. In our case, we have this extra term. So what we need to do, we have to reformulate this problem in order to get in this form and use exponential integrator. So this work was inspired by the work of Koijin to 2018. What we do, we build a projection operator, which I'm not going into the detail, and then we have our problem in this form. But this projection operator is large, so we don't want to compute it and store it. Too much memory. So first of all, we do the projection of the momentum equation in divergence-free space. We do it using a fractional step method, and then we want to apply the exponential integrator, and we use Krylov-based methods because in this way we don't have to use this compute explicitly this exponential matrix. Okay, we project everything on the Krylov subspace. So before showing the results, what we did some convergence assessment for the exponential integrator with respect to the second order Adam-Bashford we used for the homogeneous adjoint equation. So we want a problem which has just an homogeneous adjoint equation, so we can compare the two. So we have an optimal temporal energy growth in the lead-driven cavity Reynolds 1000. These are cost function. We want to maximize the energy, so we minimize the inverse. And the control is the optimal initial condition. This was an assessment. What we did, we ran this simulation for a very short time, decreasing the delta t. But in order to avoid numerical error given by the resolution of the primal problem, we solved the direct problem just once with the most refined delta t, and then we are just using the snapshot needed for the integration of the adjoint. So we use Adam-Bashford second order and exponential integrator, and that's what we can see for the error. So the Adam-Bashford is a linear behavior. This is more or less order 1, which is less than we expected, but we have many factors that introduce some error, such the fractional step method to solve the primal problem, the fact that it's the adjoint problem, the fact that we have inverse boundary. So this is the convergence of the adjoint. Huh? And then for the exponential integrator, we can see some kind of spectral behavior, which is current with what we expected, meaning that we can use larger delta t, having a lower error. We applied the parallel algorithm just on one gradient extraction, so one direct adjoint loop, and that's what we got. So here in blue, we see the time needed to compute the serial forward problem, so just the Navier-Stokes equation, direct. And here we have the time needed to compute one loop. Okay? So using the paralleling time algorithm, we can decrease the time needed to compute the gradient of about 90%, meaning that when we use the paralleling time algorithm, we have the function evaluation and the gradient almost at the same time, which means that we can reduce the time needed for the full optimization problem. So what we did, we introduced, of course, this in the full optimization and see what was happening. So we did same problem with same number of iterations in serial and in parallel. The cost is more or less the same. The time to solution is quite lower when we use just a 4 cores. And when we check the results we get, so again we have the velocity distribution, we see that it's pretty similar. The errors are given by the fact that we're using a different integrator. And also here we have still blowing and suction. But here we use the steady actuation, meaning that the control variables do not depend on time. Okay? We want to see how the algorithm scales when we use unsteady actuation. So now the control variables are time dependent. So we built a toy problem to simulate what happens in the stage of a rotor with an axial compressor. We did some approximation, of course. So we are considering a single unit casing. We simulate the blade using immerse boundary points. And in order not to move the immerse boundary points, because then it will take a lot of time to recompute all the interpolation and regularization operator between the Lagrangian points and the Cartesian grid, we decide to move the lid. We have periodic boundary condition, and we neglect any kind of curvature. So this is the flow we get. We have the vorticity and the pressure, and we see that we have many impact on the back of the blade. And the vorticity here and this impact are cause aerodynamical losses. So what we want to do is to try to uniform the pressure on the blade and reduce the gradient pressure in the front and in the back of the blade. So we use some control. We do the control. We want to add the casing roughness. So we approximate a roughness with the form of a Gaussian. And we want to control the height and the width of this Gaussian. For doing this, we can both introduce image boundary points, but again, then at every delta t, at each delta t, we have to update the position of the points. Or what we do, we use dynamic roughness, proposed by Jacobi and McKeon in 2011, in which we manipulate the boundary condition here in order to simulate the presence of the roughness. Okay? So now we have the control parameters that are epsilon and sigma, and the time dependency is given by the fact that the center moves. So these are also time dependent when we go in discrete system. So we want to reduce what we said, the delta P in front and in the back. Here we consider average delta P. Takes a little bit more time to converge, but then we manage to reduce at least the frequency of this vorticity, even if the pressure is still pretty high. So the magnitude of this vorticity here is not reduced. But now we can see that we have just one impact on the back of the blade. So this was a toy problem we used, not too much to check the physics, but to see what happens with the algorithm. Okay? Now, in this case, we reduce the time for the computation of the gradient by 58%. This is given by the fact that now the variable depends on the time. So my optimality condition at the end has an extra dimension, and depending on the type of control, we will have to compute this matrix. This takes time that we cannot avoid. So, to conclude this part, what we did, we used the parallel time algorithm applied on incompressible Navier-Stokes equation in order to reduce the computational time of an adjoint-based optimization. We tested on steady and unsteady optimization, actuation, and it shows good results on our small optimization problems. What we want to do now is to investigate unsteady actuation in a different way, based on the work of Alejandro Quiros, which is part of our team. And so we want to apply to parallelize the same optimization test case used on different regimes and see how this scales with our algorithm. So I'm going to start talking about the second part, moving away from the optimization problem. We know that complex dynamical systems are usually governed by a balance of different dynamics, okay? Dominant dynamics. This allows us to build simplified model, so to approximate equation, build reduced order model, and to build a turbulence model. As we see here, for example, we can see the flow over an island. Then we can assimilate to the flow over a cylinder. And very known in the literature, if we do an SVD decomposition, we get the POD mode without the current structure governing the flow. POD modes can be used, for example, to build reduced order models. So starting from this knowledge, nowadays we have a lot of computing power, and we can store a lot of data. So why don't we use this data to understand something more about our flows, okay? We want to use this data to do to identify the dominant dynamics present in the flows, governing the flows. This can help to build a reduced order model that are adapted on the type of dynamics that we see. This can help also the control optimization strategy, because if I know how the dynamics behave, I can put my sensor where it's more convenient. Or for data simulation, the same, we can go and focus in some region to get the data. So the main goal, what we want to do is to identify and locate different dynamics in a flow. For example, from Alejandro's flow, we have the same geometry, but we see at different regimes, the dynamics are pretty different. Okay? So we want to try to learn these dynamics, and we propose an algorithm which is based on linear regression and clustering algorithm. So, we use, again, the flow past a circular cylinder. The flow is governed by the non-dimensional incompressible Navier-Stokes equation, and we suppose, but we know, but we suppose that dominant dynamical behaviors are defined by the balance of this term in different locations of the domain. So we have the inertial forces, pressure forces, and viscous forces. What we want to do is to identify these dynamics in the domain and cluster them together. So this is the algorithm. We go with a snapshot collection. We pick some random points in the flow. We apply local linear regression at each point, and then we go clustering the points together based on the dynamics. So snapshot collection, we collect the time series and we build our matrix. Then we pick random points in the flow. Here I picked 5,000 to cover more or less the whole domain. And then we apply linear regression, which is based on equation identification in the C&D code. So the idea is that we can discover the governing equation from data. So we have a nonlinear term at the right-hand side that we don't know. So we can approximate this nonlinear term with a linear combination of candidate functions. So we build the library of candidate functions, and then we can rewrite this system like this. So we have the library of a candidate function and a set of coefficients. We want to find the value of this coefficient to check which one of these linear or nonlinear dynamics are active in our flow. So we want to identify, mathematically, we want to identify the active terms in this library. We apply this on the Navier-Stokes solver we have, so we collect the data, and from the data we compute spatial derivatives using the neighbors, up to the second order for the velocity and first order for the pressure. In this way, I can build my customized library of candidate function, and I build all the possible linear and nonlinear terms I have in my equation. In this case, I assume that I know the equation. And then I use linear regression to identify the active terms at each point. Okay? By the end of this process, at each point, I will have a set of coefficients showing me which one of these dynamics are active. For example, here I show 3 points that I assume, I think, they live in 3 different regions, and the results of my linear regression confirm my idea. So we can see that, first of all, the magnitude is reducing, moving further away from the cylinder, and some terms are disappearing. So now I know that different regions are governed by different terms, so different dynamics. Now I want to cluster my points. Imagine I have points all over the domain based on the dynamics. So I cluster on the coefficient subspace. For doing this, when we talk of clustering, first thing to try, K-means algorithm. So we compute the relative Euclidean distance in the coefficient subspace, and then we call the K-means clustering algorithm, which works pretty good. So it's currently what we expect in the cylinder flow. We always have a weight region and a free stream region with some intermediate layer. But the thing with the K-means is that the clusters are defined by the user. So how do I know a priori which one is the right number of clusters? We propose an algorithm based on network science. So we use Neumann network, and we represent our network as with nodes and edges graphically. If you want to move to the mathematical description, we have an adjacency matrix. And we have element 1 when 2 nodes are connected by an edge, and 0 otherwise. In this case, our network is undirected, unweighted, and we have no self-loops, so we can see that the adjacency matrix is symmetric with null diagonal. What happens? So neural network is uses a spectral method to identify community. So what we do, we feed the adjacency matrix in the network, in the spectral solve method, optimization method, and we use repeated bisection to find community. So first we divide the network in two, then we move to each community and we divide again until we find the optimum. The good thing about neural network with respect to K-means algorithm is that the number and the size of the cluster is not known a priori. So we build the adjacency matrix. So again, each point is a node of the graph, and now we have to put edges, to build edges. The edges are based on the relative Euclidean distance in the coefficient subspace, but since we are computing distances, we don't have 0 terms in our matrix. So we want to sparsify our graph. We remove edges, introducing a threshold. So we said that two nodes are connected to each other if their distance is smaller than a certain threshold. Otherwise, this is 0. So now we have our matrix A. We give it to the Newman algorithm, and that's what we get at the end, which is very similar to what we got with the K-means, but here we are solving an optimization problem. So again, we have a wake behind the cylinder, an intermediate layer, and a free stream region. Here we have some mixing because we are moving away from the cylinder, so the cluster starts mixing. And if we investigate the active terms, it is current with what I found before. So we have different, this is very low, but it is active. We see the different terms active. Here, everything is normalized by its own maximum value, otherwise this would be white compared to this. So we found our communities, we found our dynamics, and using a Newman network, we can now rearrange the matrix, the adjacency matrix, putting points that are in the same cluster together. And what we see is that we have some linear communication between clusters. Okay? So remember, we clustered in the coefficient subspace, but we find something coherent. Clusters that are close to each other communicate. Okay? So this is what we expected with the wake behind the cylinder. But what we will try to do is to apply that on the cascade of plate we said before, and we expect to see different dynamics, so different same dynamics located at different location, spatial domain in the domain. So then we could see different regions behaving in the same way, and also see how they interact to each other. So if I know that if I want to modify something here, I can put some control here, and then this will affect the dynamics here, I can have the optimization procedure. So, to conclude the second part, very short. So we used the Newman network to identify different dynamics in fluid system, and we use this with Navier-Stokes equation, and we use a linear regression step to identify the active dynamics at different regions of the domain. And we want to extend this algorithm on a more complex application, first into 2D with different regimes, and then eventually in 3D compressible. And some perspective now, conclusion is perspective. So the goal we set at the beginning was to use some strategies to reduce the computational cost or the time cost of CFD with optimization. So we used some strategies and we got some pretty promising results. The proposed algorithm can be used both on derivative-free and gradient-based optimization, and we want to extend in the future this algorithm on more complex application. And now some perspective. So we said that the knowledge of different dynamics can help the use of reduced order model, selection of design parameters for the optimization, and sensor placement. Here, so we investigated a little bit model reduction with the GNAT method. GNAT method performs when hyper reduction, approximating some tensors using greedy points. So we have an algorithm that selects these points according to the region where the nonlinearities are more frequent, we could say, where the linear projection doesn't work very well. So here, if we compare the two, we can see that the points are actually selected in the nonlinear region. So the idea that we are developing right now is that if we use this dynamical identification as a pre-processing tool to understand if we can use a reduced order model, if a linear reduced order model is enough, or we have to apply some hyperreduction or some linear adjustment, we will know it before. So what we would like to do in the future is to build a code that first runs dynamic identification, and then according to the results we get, how do you say, use or not reduced order model, so activate multi-fidélité dynamics, and also we have a derivative-free solver in the team, so we want to build something that say, okay, here the dynamic is too complex, we cannot use adjoint, move to the derivative-free, or we can use adjoint, but we can reduce the time, use the parallel time, and have something dynamical that can adapt according to the existing dynamics. And thank you for your attention.
Okay, thank you very much for the presentation. We now start with maybe we'll wait a few minutes so that people will hear.